Greetings, statistics scholars, and welcome to a video dealing with inferences involving differences in means when we have paired data. This video accompanies section 6.5 of our text from Locke. I want to begin this video by indicating that whenever we're doing inferences involving differences in means, it's very important to be careful to distinguish between situations where we have means from two separate independent populations and when we have two means that are coming from the same sample, what we call paired data. Consider the following two different situations. In the first scenario, suppose that you're doing an experiment involving a sample of 30 rabbits and 30 turtles. And you're going to time each of these to see how fast they move to their food source. You decide that you want to compare the difference in the average times that the rabbits take to move to the food to the average time that the turtles take to move to the food. In this particular case, it's a problem involving a difference in means. This is a case of what we call two independent samples. We have a group of 30 rabbits and another group, a separate sample of 30 creatures that are clearly different in nature from the first. We call this independent populations. But now consider the following situation that also involves two averages. Suppose that you do an experiment where you have a sample of 40 rats, and you time those rats. First, as they make their way to the exit of a maze without the influence of any kind of medication, and then a day later, while those rats are under the influence of a drug, you time them again. And you compare the difference in the average times that the 40 rats take to exit the maze. First, the average time when they didn't have the medication versus the average time when they did have the medication. Now, in this situation, we don't have two different populations. We have only one population, the rats, and only one sample. And we're taking multiple measurements from the same sample. This is a case of what we call paired data. The samples that we have are not independent of one another, as we had in the case with the rabbits and the turtles. We have paired dependent data. It's important to distinguish, very important to distinguish between these two situations, because we're going to do inference differently in them. In the first situation, such as with the rabbits and the turtles, we're talking about using the difference in sample means as the statistic of interest. Because there are two separate populations and two separate samples, it makes sense to talk about an X1 bar and an X2 bar, two separate sample means. And we look at the difference in the sample means, and our standard error is computed using a formula that uses a sample standard deviation from the first group and a separate sample standard deviation from the other group. So in this particular case, if we were working with independent populations and two independent samples, then we take as our statistic the difference in the means. But what if we have a situation as with our rats? In the situation with our rats, we don't really have two different populations. We only have one. So it doesn't make sense really to talk about more than one mean. What we're going to do in this case is we're going to look at the differences between the two observations for each of the individuals in the sample, and we'll take a look at the average differences. Now make a note there how we've changed the order of the wording. When we have independent populations, we look at the difference in the means. But when we have only one population with paired data, rather than the difference in the means, we look at the mean of the differences. In this case, our standard error is just going to use the familiar formula from section 6.2. After all, if you have only one population, it doesn't make sense to talk about S1 and S2. Instead, we'll just take a look at the standard deviation of the differences in the values. And we'll use our formula, familiar formula, from section 6.2 to calculate the standard error from this one population. So let's take a look now at an example of creating a confidence interval for differences in means when we have paired data. Consider, for example, the following scenario. Suppose there's a large college French class with hundreds of students, and they're taking a quiz on regular ER verb conjugations. They're actually going to take the quiz 2 times. They'll take the quiz first, and then a day later, after watching an instructional video as part of the course, they retake the same quiz. Now you take a sample of a dozen students from that class and take a look at their scores before and after the video. And let's suppose they're tabulated as shown here, so that, for example, student A, who had only a score of 32 before watching the video, rocketed up to a passing score of 70 after watching the video. Student B, who had scored a 76 initially, showed a more modest but still a gain up to 88 points after watching the video, and so on and so forth. And let's suppose we want to create a confidence interval involving the difference in the average scores of the students in the entire class. Based off of this sample of 12 students, let's make a 90% confidence interval for the difference in average quiz score after the video compared to before the video. Now we're going to create this using our standard approach. We'll find a statistic that we'll put right in the middle of the interval. That will be our best estimate of the average difference. And then we'll figure out a margin of error that we'll add and subtract to that to get our limits. Now here in this case, since we're dealing with averages, we expect that margin of error, ME, will be some t-score times the standard error of our statistic. We clearly have paired data here. This is not like the situation of the rabbits and the turtles. It's more like the situation of the rats. We don't have two independent populations. We have only one, the students who are in the French class. And we have two measurements being taken from individuals from that same population. So as we said before, rather than looking at the mean of the differences, we're instead going to turn around the order of that and talk about, rather than talking about the difference of the means, we're going to turn that around and talk about the mean of the differences. Let's look at what those differences are. For example, student A went from a 32 to a 70. So what was the difference in their scores? Well, 70 minus 32 after minus before, in this case would be 38, an improvement of 38 points. For student B, they went up to a score of 88 from an initial score of 76. So 88 minus 76 is a difference of positive 12. And we'll compute those out for all of the students. We note when we do that most of the students, labeled A through M, demonstrated an increase in their score. And we did have the occasional student, such as student G, who went from a score of 75 to 73, resulting in a negative difference. But by and large, the video seems like it was useful because in most cases, these differences are positive. What we want to do, though, is to create a confidence interval for how much we think that difference was on average for all of the students in the entire class on the basis of these 12. Let's go and see where this leads us. The statistic of interest, as we said, is the average of the differences, not the difference of the averages. So we're going to compute what we call D bar. D bar here is the average of all those 12 differences. If we add up 38 and 12 and -5 and 44 and so on, if we add up the differences, we get 173. Divided by 12, that gives us an average difference of about 14.417. That is our statistic. That is the value that will go in the center of our interval. We will build the confidence around the average of the differences, 14.417. Now, of course, having ascertained where the center of the interval is, we need to know how wide we need to make the interval. If we wish to be 90% confident, how big of a margin of error do we need? That is the crucial next question we must answer. That, of course, hinges on what sort of distribution our sample statistics have. We had 12 differences in our sample, a sample of size 12. So that means that when we come up with the t star value for determining our margin of error, we're going to want to use a t distribution with 12 minus 1 or 11 degrees of freedom. We consult StatKey or some other statistical software, and we determine that for a t distribution with 11 degrees of freedom, we need to use the value t star of 1.796 in order to assure a 90% confidence level for that particular kind of t distribution. So in computing our margin of error will be 1.796 times whatever the standard error of our statistic is. Which begs the question, what is that standard error? What is the standard error of our statistic? We said earlier, remember, that we would be using the formula that comes when we work with means from a single population, not the more complicated formula when we have means from two independent populations. That formula simply says that the standard error is the sample standard deviation divided by the square root of the sample size. So here it will be the sample standard deviation of the differences divided by the square root of 12. But we need to know what that sample standard deviation of the differences is in order to finish off that calculation. So how can we know what the sample standard deviation is for this set of 12 numbers? For 38 and 12 and -5 and 44 and so on, what is the standard deviation of that data set? Well, recall that we can use the one quantitative variable option in StatKey's first column to compute various statistics about a variable, including its sample standard deviation. So if we go to StatKey and choose one quantitative variable, I can enter a data set. And here you can see we put in our 12 individuals, A through M, and the size of their differences, 38, 12, -5, 44, and so on. Having put that data in, once we hit enter, StatKey will be quick to run an analysis of that data set. You can see here it's showing various summary statistics. Sample was size 12. You can see the average value that we had found earlier, confirming the 14.417 value that's in the center of our interval. Other things like quartiles and medians, but what we're most interested in here is the sample standard deviation, 15.722. That's the value that we will use in helping to calculate our standard error. That's the number that goes in the numerator of our standard error formula, 15.722. Let's finish that computation now. Standard error is S divided by the square root of n when we're dealing with the single population mean. So 15.722 divided by the square root of 12 turns out to be a little bit over 4.5. We can now take that value and substitute it into our margin of error formula. We'll replace SE with 4.5386. And in doing so, we'll find out that the margin of error for our interval should be a little bit over 8 points, about 8.151. We now have everything that we need to finish our interval. If the margin of error is 8.151, well, what will the lower limit of the interval be? It'll be our statistic, our D bar value, 14.417, minus our margin of error of 8.151. And so that gives us a lower limit of a little bit over 6 points, 6.266. On the other end of the spectrum, For our upper limit for the confidence interval, we add the margin of error, 8.151 to the D bar value. When we put those two together, we're going to find an upper limit that's a little bit more than 22 points, about 22.568. So we now have the range of values for the confidence interval for the class at large. And that's important to remember what we're doing here. Remember that we started with a sample of 12 students. Those weren't all the students in the French class, they were only a selection of them. But based off of that selection and based off of analyzing their differences in scores, we're now prepared to make a generalized statement about the class as a whole. We're going to say that we are 90% confident that the average difference in scores from after the video compared to before the video on this verb quiz for the French class students was somewhere between 6.266 points and 22.568 points. Clearly, the video was effective in increasing the overall scores for the class at large. I thank you for your attention here, and we hope that this video has been instructive and useful to you as you work on the idea of making and doing inferences when we have means and when we have paired data as opposed to having two independent populations.